Hello, hello. So, I'm assuming you, the viewer, are either A, one of my current students, or B, some random person on YouTube who probably has a chem test tomorrow over kinetics and is looking for a crash course. So, please treat this video as a introduction into kinetics. It's not going to go too in depth on some of the more advanced problems, but it should serve as a good foundation for the theory, the formulas, and the basic type of problems you will see in the kinetics unit. So without further ado, I usually start this unit by going over what the heck even is kinetics. So we are talking about kinetics, which, if you know from maybe a previous science class, kinetic refers to movement. And while we're not talking about quite an atom literally moving, we are talking about the movement of a reaction, so to speak. Let's say we just had acid base with my students, so I'm just in that mood. Let's talk about some good old acid base. I'm assuming you probably have done equilibrium if you are doing kinetics. If not, worry not. This is not required to solve this problem, and I apparently don't know chemistry because I just said an acid makes hydroxide. Excuse me for my little brain fart. So here we have a typical reaction, right? And what we've talked about so far is stuff like stoichiometry. So if I have 0.1 moles of this guy, well, it's equilibrium, so I'll probably need molar. But if I have a certain amount of my reactants, I can calculate how much of my products I will make, whether that's stoichiometry with a solid arrow reaction, you know, a one-way street, or if it's equilibrium, it doesn't matter. Up to this point, you should be able to calculate the amount. Well, that's not what we're talking about. I don't care about amounts. I don't care how many moles you have. I care about how fast I am creating my products. I care about how quickly my reaction's proceeding, because some reactions are very fast. You know, if I light a match and then drop it on some gasoline, I'm going to see combustion fairly fast, right? But some reactions are much slower. Something like, for example, iron rusting takes a lot of time. And this unit will be going over how we can make sense of different reactions having different speeds. So one thing we talk about in this unit of kinetics is something called a rate order. And assuming you've been to lecture one time, you've probably at least heard of the idea of an order, right? It's not commonly explained too in depth by professors and teachers, which I find problematic. So let me take a stab at it. When we're looking at reactions, if I were to try to zoom in and visualize it atomically, right? Let's say I have a simple reaction like 2A plus 1B makes A2B. Something super simple, right? If I were to try to draw this visually, what's really happening is I have two A atoms and I have one B atom. And they're going to collide. If you haven't heard about this earlier in the course, you might have heard this term or this idea of collision theory be mentioned. We know we need our atoms to collide to react, right? Obviously, if I need A and B to react, they got to go touch each other and react. They can't just react across the room. So our atoms have to physically touch, they have to collide with each other. And there's another requirement of where they need a certain amount of energy. We usually refer to this as the activation energy, right? So you need enough energy and you need a collision, smack together, bam! And that would create my A2B, which I'm just going to draw as if it looked like water because I'm just going to make up some type of geometry for it. Not too important. But the important idea here is we're zooming in on this part. This is the part we are concerned about when we discuss rate order. So right here, I can see that I have two A molecules colliding with one B molecule or one B atom and two A atoms. That means that this reaction is second order with respect to A because there is in fact two A atoms colliding. And meanwhile, with respect to reagent B, this would be a first order reaction. For those of you who are a little bit more ahead in the units, I'm assuming this is the rate determining step. For those of you who don't know what the crap I just said, sit tight and we'll get there. So I hope this makes sense so far. For this reaction, I have to have two A's and one B collide. Because I'm assuming that's the rate determining step, that means for this reaction, A would be second order, B would be first order. The order pretty much just refers to, at the important step, how many atoms are taking part in that reaction, right? So if I'm assuming a one-step reaction, I have 3 total atoms. So sometimes we refer to something called an overall order. My overall order is simply the sum of all the other orders, which is third, because you can clearly see I have 1, 2, and 3 atoms taking place in the reaction, right? 1b, 2a. With that out of the way, I hope you understand at least what rate order kind of refers to. Now let's dig into the 3 main rate orders we'll be working with and all those lovely formulas and all those lovely ideas, excuse me for tripping over my words, that we usually talk about with our rate laws. So, I like to draw this little chart. At the top, I'm going to write 0, 1, and 2. And I give 2 a little more real estate. So, let's assume for this entire discussion, I have a super, super simple reaction, something like A goes to B. The reaction really doesn't matter. All you need to care about is that I have one reactant and it's A, okay? So, off the bat, I'm going to give you a little mnemonic, clear. Sadly, there's no vowels in clear. You'll see why in a second. But CLR. C goes with 0, L goes with 1, R goes with 2. And we have these things called rate laws. What a rate law is a formula that will help me to write how I can calculate the actual rate of a reaction. Rate laws all have the same skeleton. They all look very similar. Very simply, rate equals K. This is a different K than your equilibrium. It's usually lowercase, so I'm going to try to write it super tiny to emphasize that. It's a different K than your equilibrium K. This is our rate constant K. And you're going to multiply K by the concentration of whatever reactant you have. In this case, I only have A, so I have A right here. And just like in your equilibrium unit, or similarly, it's a little different, I'm going to raise this concentration to a power. And I'm just going to put X here because it's variable. X is whatever the order is of A. So for example, now in my chart, if I assume that A was 0 order, my rate law would be rate equals K times A to the 0 power. My first order rate law would be that rate equals K times A to the first power. And if it were second order, my rate law would be rate equals K times the concentration of A to the second power. It's very, very simple, assuming I give you the rate to write the rate law, right? And keep in mind, we only care about reactants. Rate cares about reactants, RR. So B will never show up in any of my equations over here. I don't really care about B. He's doing his best, no offense to him, but I don't really care. Now, that is the normal rate law. We don't do too much math with this, to be quite honest. We will be writing regular rate laws a lot. Sometimes I call it a regular rate law to differentiate it from the real King Papa that we will be talking about at length in this unit, the integrated rate law. Now, I'll elaborate on what this integrated business means. But for now, just know it's a different type of rate law. And anytime you're doing some math and calculating, actual concentrations, this is probably the guy you're talking about. Now I'm gonna give this some more room. And normally these will all 3 be present on your formula sheet. If it's not, I'll go over a quick way to help you memorize it. So the first integrated rate law, I'm not going to go over how to derive it. Frankly, I'm lazy and I don't quite have the exact idea of how to do that for some of these off the top of my head. So let's not go over the derivation of these formulas. I'm just going to present them. So for your 0 order, you have your initial concentration, or my apologies, your final concentration is equal to negative K times T, where T is the time your reaction is going on, plus your initial concentration. I'm going to go ahead and dig into why we call this an integrated rate law. We call it integrated because we kind of moved it around in a sense where it mirrors y equals mx plus b. And if you've ever seen the graph of these bad boys, for a zero order, we graph concentration on the y-axis, we graph time on the x-axis, and it's going to look something like this. Which, what is this graph showing? It's showing that I have some initial concentration and I started out at my peak, right? Let's say I started with 3 molarity of reactants. Well, as my reaction goes, it makes sense that I'm going to be using my reactants. So I have a negative slope, as evidenced by this negative KT right here, and I'm going to be losing concentration. And eventually I am probably going to run out, assuming my reaction goes to completion, which is fully possible. So what you can see is if I graph based on this equation, if I graph my integrated rate law, it becomes linear. And that's true for all 3 of them. If I were to show you the other 2, excuse me, real quick, you can see that the integrated rate law also looks really similar. First order is natural log, ln, and that is where the clear, the CLR from earlier comes in. C stands for concentration. L stands for natural log, because when you go to your integrated rate law, all you're doing is taking your zero order and slapping a natural log in front of your concentrations. It is the exact same otherwise. Again, normally this is on your formula sheet, so I hope for your case it is. If it's not, lock in and memorize. Memorize your zero order, and then just know you slap an ln in front. And then the R for second order is for reciprocal, like a fraction. So instead of being concentration of A final, it's going to be 1 over the concentration of A final. Other weird thing, this one's positive. We'll talk. We'll get there. I'm kind of info dumping a whole bunch at you, I know. That's kind of what this unit is. So here are my 3 formulas. Notice the similarities. Notice you can kind of take this as your skeleton and just do CLR and change it, except for this little jerk right here. I'll go ahead and erase this graph. Hope that's okay. We'll talk more about graphs later. But these are your integrated rate laws. And I guess to talk about why these are important, let me show you what happens with first order, for example, right? So as shown on the left earlier that I just erased, normally for zero order, you graph concentration, right? Well, what happens if I graph the wrong order? So for example, if I were to assume that A was first order, and I tried to graph him on concentration, which is for zero order, right? If I were to try to force that to happen, you're going to see a really goofy graph. And that is not linear. This is a non-linear graph, so I know this is a waste of my time. This is not proper. I am not zero order. This is effectively useless in a lot of ways. So I don't really care. But if I were to graph it versus natural log of concentration, suddenly it looks very familiar. That is the exact same looking graph as before, right? It's just a negative linear plot. That is why we integrate. The whole purpose of integration is so we get this, right? Second order is a little weird. Talk about him. He's the only one with a positive slope. And the reasoning is a little strange at first. For my students and listeners who are more mathematically inclined, you might already understand why. It has to do with the fact that we are a reciprocal graph. So I already spilled the beans that it's positive slope, right? Let me prove to you why. Let's assign a point to our time equals 0, right? Let's say this is like 0, I don't know, 10. Just to say this is 10. Up here would be something like, I don't know, 5, 20. just to make up some numbers. This looks like my concentration is increasing, but let's examine that a little deeper. At time equals 0, my 1 over concentration is 10. That means my concentration is 1 over 10. If I were to solve for x, right, for the brackets, it'd be 0.1 molar. Okay, and then at time equals 5, my 1 over concentration would be 20. Okay, that means my concentration is 1 over 20, which is 0.05. So my concentration, although it looks like it went up on the graph, actually went down. And that's because it's a reciprocal graph. So the larger y value is, actually the smaller your concentration is. If that doesn't make sense, don't sweat it. Math is lame anyway. So this is a big fat info dump of your important formulas. Whether or not you have to memorize it is entirely up to your individual professor / teacher. I wish you luck in the draw. I pray for good formula sheets for all of you. There's one more little thing I like to add to this little chart, and that's the special properties of each of these guys. Each rate order has something a little peculiar about it. And we've already talked about one of them. With second order, it's not a whole bunch to go into, but just the slope is positive. Kind of is a little bit to get into, already did, but slope is positive. Don't forget that. If you ever see a positive slope and it's a straight line, second order, move on with your day. Easy peasy. Zero order is really interesting, and it's probably obvious to, once again, my more mathematically inclined listeners, but anything to the 0 power is just 1. So I can just erase all this, and my rate for a 0 order reaction just equals k. And that's always true. For a 0 order reaction, your rate is constant. Which might sound duh, but a very common trick question you might get hit with is, what if I double the concentration of A? I don't care. So even if you change, the key idea here is it's independent of concentration. So I don't care if I have 1 mole. I don't care if I have 1,000,000 moles. I'm going to go the same speed, whatever k is. Whether k is 1,000,000 miles per hour or 0, I will be going that speed no matter the concentration of my reactants. Doesn't matter. First order is interesting, and we're just going to leave a little star here, and we're going to come back. For my more advanced students who are using this as a review, half-life. For those of you who don't know what that word means, let's dig in. Let's do some actual math now. Please feel free to back up in the video and look at that chart as a cheat sheet, or if you took your own notes or a screenshot, whatever, I don't care. But referring to the chart could be very beneficial for you, so you can follow along the formulas, make your own decisions, blah, blah, blah. So let's look at a very simple example question that we're going to talk about some different rate ideas. I didn't talk about this too much because I feel this thing is really kind of obvious and intuitive, but you know, I've been doing this for years, so maybe what I find easy isn't. But regardless, let's say I have a simple reaction, right? A plus 2B goes to 3C plus 4D. Now, we've done Stoic for a while, so if I tell you I used 2 moles of A, I'm sure you guys could tell me that means you also need to use 4 moles of B, and you will create 6 moles of C and 8 moles of D, right? Just good old stoichiometry using our ratio of our coefficients. Nice and easy stuff. Well, that also holds true in our rate law world. So for example, let's say I told you, I looked at A and I could tell you A is changing. It has a rate of disappearance. I notice I am losing 0.2 molarity per second. So every single second that passes, I am losing 0.2 molarity, of A, and it's being reacted, right? Well, what must the speed of B be then? What's the rate of my second reagent, of my other reactant? Well, it's just like your stoic. It's 0.4. It is no difference. Because this is a 1, I can hop in some dimensional analysis. I can say 0.2 molarity of A per 1 second. And then I can say, well, for every 1 molarity of A, you need 2 molarity of B. Cross out A, cross out A. Now I'm just in molarity of B per second, which is the unit I want. And I get 0.4 molarity of B per second. And with the same idea, yes, it's 0.6 molarity per second for C. It's 0.8 molarity per second for D. Pretty straightforward stuff. Very similar to what you've been doing in Stoic before. Now let's get into the integrated rate law stuff. Why is this important? Because you might get asked questions like this. All right, you have a reaction. I like to keep things simple and just say A goes to B because the elemental species really doesn't matter. I tell you this is a 0 order reaction with respect to A. What that means is that A is 0 order. I'm going to tell you a whole bunch of random information. Let's say I tell you you initially had 10 molarity of A. That's quite a bit. The K for this reaction is 0.3 molarity per second. And I want to know how much is left after, I don't know, let's do 30 seconds. I asked you, what is your final concentration of A? Now, of course, I have this nice and blocked off neatly where I labeled all of my variables that I will need. And I recommend doing that, dissecting your word problem. You know, think about the words I said and then what I wrote. Get used to that process. But I pretty much have it spelled out pretty cleanly for you. The only real question is, what formula am I using? How do I even approach this? Well, I told you it's 0 order. And you know we are looking for final concentration. So I'm going to go refer to my cheat sheet real quick. All right, I got a 0 order. So I'm looking all the way in the left column. I'm in this column. And I'm looking for initial concentration. The only formula I see that has initial concentration is right there. So I'm going to go ahead and steal that. So I think we are going to be using my 0 order integrated rate law, which is that the concentration of A at the end of my reaction is equal to negative K times the time plus the initial concentration. So now I can plug in some numbers. My final is what I'm solving for, so I'll just plug in X. Negative K is 0.3. I am being lazy and not writing units. Time is 30 seconds. And my initial concentration is 10 molarity. So now if I just do a little bit of math, 0.3 times 30 is 9. There's a negative sign in front of it, so I have negative 9 plus 10. For X, I have a final concentration of 1 molarity. Or 1 molar of whatever the crap A is, right? So, awesome. And I guess as a little pop quiz, how much B would be created? I'll give you a little do. Yeah, it's 9. It's a 1-to-1 ratio. Don't forget your stoic. If I used 9, that means I still had to create 9. You probably won't get asked something like this on an exam in this unit, but, you know, for your final or just to have a nice, well-rounded knowledge base. But this is an example question of how to use an integrated rate law. I could change any of these things. It doesn't matter. I'm probably going to give you all of these things except for one, and then you just plug and chug for the missing one. It's really not that bad. There is one thing that can be a little tricky though. You need the order, and usually it will be given to you pretty directly, at least in my experience with other students. Most professors / teachers aren't trying to get you on the gotcha of, Haha, I hid the order. They want to check that you know what formula to use, what math to do, etc. However, they can. I could have not told you this, and you still could have solved. You could have been given just this information, and you have enough to complete it. That's because of your K units. This is another difference from the equilibrium unit, is our K actually has units. Now, this is a little confusing for some, so I'm going to try to break this down in a really simple way. I think of the default order as 0. I just treat 0 as like my home base. I have everything of him memorized, and then I just change it around with that clear business, right, to get my integrated rate laws. I'm going to do the same thing for my K units, because the K units for 0 order just make sense. We're talking about the rate of a reaction. So this looks like miles per hour, kind of, right? You have a unit per time, and here we're doing molarity per second. So 0 order is molarity per second. Every order you go up, you're going to divide by another molarity. So this is molarity per second with a molarity on bottom, which means those cancel, and the K units for first order is 1 over seconds. If I go to second order, I'm going to once again just start at the beginning, write down 0 order, molarity per second. I have second order, so I'm going to write m squared. If you want to write 2 m's, be my guest. That's fine. And we still cancel one of them. And now second order's K is 1 over m times s. Pop quiz. What would sixth order be? What would the units of K be for sixth order? I'm going to once again give you a couple seconds. Pause the video if you want to keep going, because I'm starting. Once again, begin with molarity per second. Then I'm going to divide for each order I have. I'm just going to go ahead and write m to the sixth. M to the first over m to the sixth. 1 minus 6 is negative 5. So I know I have 5 down here with the seconds. I hope this breakdown makes sense. This is how I do it, just because it's simple to me. So even though I didn't tell you the order up here, I gave you units of K. And because it's molarity per second, that's how you can tell me that is 0 order. Let's try another example. I'm not going to change the reaction. I'm not going to change the K, aside from, whoops, that's not white, aside from doing this. It's a very thick one. All I did was change the units of my K, and, you know, I'll give you a second to think about what order is it now. There kind of was a spoiler on the board, but this is first order. If you got it, very good. If not, good try. So this is a first order reaction. What does that change? I only changed the order. Well, let's just do the same steps, right? So I have all this information. I need a final, and I know I'm first order. I'm going to consult my cheat sheet once again. Cheat sheet, what do you got for me in the first order column? I need final concentration. Well, it's a little out of the way, but I do see you hidden in that formula. So cool, I'm going to steal this formula. Notice it is still the integrated rate law. That is common. So we are going to use that rate law we just got, which was the natural log of my final concentration, excuse me, minus KT plus the natural log of the initial. And excuse me over here, need the real estate. Let's plug and chug. So no different than before. We're just going to plug in ln of x, that's what I'm solving for, negative 0.3 times 30 plus the natural log of 10. And ln of x equals negative 9 plus the natural log of 10. I'm not getting my calculator out, but that's just a number. Don't freak out. Let your calculator deal with it. Keep enough sig figs. You know, if it's like 3.1456, keep enough digits to not make a rounding error. But whatever number that is, how do I undo a log? Very good. E to the power of -9 plus ln of 10. Whatever that number is. I'm too lazy to go calculate it. So that would be my final concentration, whatever that is. I'm not expecting a big number personally. This is probably super tiny. Anywho. These are the basic kind of questions where you will use an integrated rate law. There's one more type of question I want to go over, at least for this video. I'm going to keep the same idea. Simple reaction A goes to B. And I'm going to give you some information. I'm going to tell you the initial. That is way too thick a pen. I'm going to tell you the initial. I'm going to keep it at 10. I'm going to tell you K. I'm going to make it 0.5 this time. I'm going to keep it 1 over S. Think about what order that is while I give you more information. And that's actually all I have to give you, because I'm going to ask you for that half-life business I teased earlier. What is a half-life? And for those of you who are still working, I'm about to say the order. This is first order once again, 1 over S still. Anywho, so what's a half-life? Well, let's say that I have something radioactive, and I'm bringing up radioactivity just because that's a common example. This is where we usually see it. Think of like a brick of uranium. First radioactive dude I think of. Big old green shiny rock like it's some kryptonite for Superman, right? So what radioactive means is that it decays. It means over time it disappears. So maybe on day 100, or day 1, excuse me, I have 100%. Maybe like 400 million years later, I only have 30%. As time goes, I'm losing some. A half-life is referring to the time it takes to cut your initial amount in half perfectly. Okay, how the heck do I calculate that? Because let's take a step back. Well, it's first order, right? And based on the last question, I'm probably just going to use that same integrated rate law. So ln of my A final equals negative KT plus ln of my initial, right? That's the same formula. Let's just plug and chug. I don't know my final. That's okay. X equals negative K times, I don't know T either. So if I were to finish plugging in, you'll notice an issue where we got 2 unknowns. So let's think about something. Am I able to figure out my my final concentration? Well, it's a half-life. If my initial was 10, my final must be 5. So this actually is not an unknown. This is a fully known number. This is the ln of 5. And now it's just a one variable equation. Plug and chug, it's no different. Logarithm math might scare some of my students, so I'm going to go nice and slow. My first step would be to subtract natural log from both sides, natural log 10. So now I have ln of 5 minus the ln of 10 equals negative 0.5 times t. Subtraction of logs is the same thing as writing division. So this is ln of 5 over 10. Keep on writing. 5 over 10 is the same thing as 1/2. That's funny. I'm doing a half-life and I just got a 1/2. That's fun. Anywho, negative 0.5 times t. I'm a super nerd and I have the natural log of a half memorized. You don't have to. You have a calculator for a reason. And so t equals negative 0.693 over negative 0.5. That's going to flip positive and be like 1.386 if my mental math is correct. And that would be seconds. Why is it seconds? If we look back at our units of all of our dudes, which I know I did not write, that's molarity. This right here is 1 over seconds. And this right here would be molarity. When we have this molarity over molarity step, you'll notice my units cancel. So the only unit I have left is 1 over seconds. And then we divide by 1 over seconds. So 1 over 1 over seconds. Dividing by a fraction is the same thing as multiplying by the reciprocal, right? This is the same thing. 1 times seconds over 1, or just seconds. Anywho, that would be my answer to this question. One thing that's really interesting is half-lives for certain orders vary based on different things. So for funsies, I'm going to keep this number right here. I'll circle it in red. Let's go ahead and erase everything else. And let's do a very similar problem. Let's change a few things and let's see what happens. So let's say that instead of 10 initial, I have 100. Let's just slap a 0, right? Well, we can kind of fill in the final here. We know it's still a half-life, so I'm going to have 50 instead of 5. It's still the same original equation. Plug and chug. I'm going to plug in my final concentration, which is 50 in this case. My K is 0.5. My T is what I'm solving for, so leave that alone. And my initial is 100. Once again, my first step is I'm going to subtract the natural log of 100. So I get natural log of 50 minus the natural log of 100 equals negative 0.5 times t. Subtraction of logarithms is the same thing as division. So that's the ln of, oh, this looks really familiar. This looks extremely familiar. And that's because welcome to the special property of first order reactions. The special property of first order reactions is that, let me flip over, fill in our chart. Half-lives are constant. So for 0 order, the rate is constant, right? Doesn't matter your concentration. For first order, half-life is constant. And once again, that key phrase that you might see as a multiple choice answer, independence from concentration. And just like that, the fully filled in chart with all that good stuff. So I hope this served as at least a decent overview of the unit, giving you all your formulas, giving you your two kind of easy, your too simple form of question. There is more in this unit, but I wanted to let this serve as a overview before digging in deeper into the unit. So I hope this video was helpful. If you have any questions, comments, or concerns, please feel free to, if you are a student, text me. And if you're some person who found this on YouTube, please comment away. I will happily try to respond to every single comment I see. Thank you for your time, and I hope this is helpful. Goodbye.